Hello and welcome back to a summary episode of episodes 1 to 7. So, this is episode 8. This will be a summary of all the different topics we touched upon in episode 1 to 7. So, this is a good point to pause and look at what we have learned. So, we talked about how a AI model learns, how do we teach an AI model to understand our world, how do we feed it data. We talked about tokens, language models, transformer architecture, and we also questioned whether AI is really intelligent or is it just an illusion. So what I've done now is I've taken all our previous episodes and run it through Notebook LM to generate a nice summary. And most importantly, Notebook LM can also generate a kind of a debate or a, let's say, a discussion around the topics we have covered. And it has come out so nice, I actually wanted to listen to it along with everybody. So what I'm going to do now is just play the discussion that I have downloaded, and I also have a few slides which summarizes the last few sessions we had. So let's get into it. I'm going to listen to it along with you, and we can jump in where needed to have some short discussion.
Welcome to the deep dive. Today, we are really cracking open the hood of, what's probably the most impactful technology of the last decade, modern generative AI.
Definitely.
If you spend any time using tools like ChatGPT or, Copilot, you know the power they have. But today, we want to move past the interface.
Right.
Go straight into the architecture. You provided us with sources that, honestly, offer a masterclass in the foundational science behind these systems.
And that's really our mission here. We want to transition you from being just a user of AI applications, to truly understanding the hidden intelligence that's actually powering them.
Okay.
We need to look at the foundational models, and also the specific architecture, the transformer that makes all this modern AI possible.
And the very first nugget we pulled out, it seems crucial for just resetting expectations.
Yeah.
But what we're actually interacting with. That friendly chat window you use, that's not the intelligence itself, is it?
No, absolutely not. The application interface,
So one thing to note, the discussion is so lively and it feels like you're actually listening to some kind of a radio show. Fantastically done. So you eventually tend to forget that it is generated from your own content. So in our case, we took the last 7 episodes, fed it through Notebook LM to come up with its summaries, and then we asked it to generate a good debate based on the topics. You completely tend to forget that this is a AI generated summary and debate. So let's get on.
text box you type into, it's really just a thin presentation layer.
Yep.
If you look at systems like ChatGPT, the core value, the knowledge, the intelligence, it resides entirely in the large language model, the LLM, sitting behind that interface.
Right, behind the curtain.
Exactly. The application just handles the input and output. The foundational model is the brain doing the actual work.
Okay, so let's unpack how that brain works then. We have to start with a concept that is, surprisingly old, almost Victorian in its roots. Statistical prediction.
It's fascinating, isn't it, how far back this goes? Our sources reminded us that the core idea is just simple pattern recognition. The history here is great. Think back to Sherlock Holmes.
Oh, yeah.
Remember how he could deduce a coded message just by noting that the most common recurring letter had to be E?
That's a great example, just frequency.
Just frequency. And this statistical approach became essential in the real world too. Claude Shannon, decades later, used similar statistical concepts to help decipher messages during World War II.
So he wasn't decoding based on context or meaning, just pure statistics.
Purely based on frequency and likelihood. And that is the basis of a language model. Observing repeating patterns like which words or letters often occur together to build this huge statistical map of the language.
So a large language model, an LLM, just scales that idea massively.
Massively, by feeding it enormous data sets. Novels, scientific journals, Wikipedia, business documents, you name it.
But it's important to stress here, right? The model isn't...
See, that's the beauty of AI going through our content and coming up with its own interpretation of or with its own way of presenting that information. So we did talk about how we trace this back to early statistical analysis of a language, and Sherlock Holmes was an example I used. But here in this discussion, the host and the other speaker, they kind of weave it very nicely into a lively discussion. I think They do a much better job than me. So let's just enjoy it.
Thinking or understanding like we do, it's building statistical relationships.
Precisely. It learns that if it sees the word trace, the word back has a statistically high chance of appearing next, or that roots often precedes trace back.
Just based on seeing it millions of times in the data.
Exactly. It retains these relationships based purely on probability, and that allows the model to easily predict what might come next in a sequence.
Okay, and this prediction ability, it requires massive computing power to train, right? That led to this idea of the foundation model.
Yeah, the resource cost is immense. We're talking billions of dollars worth of compute and data, so the industry quickly realized it didn't make sense for everyone to start from scratch.
Right, wasted effort.
Totally. So foundation models are trained once on these vast general data sets. They become commercially available building blocks, often accessed through APIs.
That makes sense, like a pre-built engine.
It's the genius of the business model, really. You don't have to rebuild the entire machine. You take this giant pre-trained brain, and then you can tweak it or fine-tune it for your specific task.
Like summarizing medical notes, maybe, or
Sure.
generating marketing copy.
Exactly, those kinds of specialized, task-oriented applications. It saves everyone massive resource costs. Oriented applications.
We have covered a lot of these things in our foundation models episode. There's a lot more details there. And one other thing that I just wanted to tell all the people who are looking at these episodes is that if you want to cover or understand the models, these videos are a great place. You can get a good understanding of it. But if you want to go really deep down, nothing really beats picking up a book and going through that in detail. I would recommend Chip Hoyen's AI Engineering. I refer to that throughout these episodes. Of course, there are a lot more books we can go into, but this is a good place to start, especially to understand this whole landscape of AI. Just wanted to drop it in there.
Okay, so if the model's entire existence is built on this continuous prediction, we have to talk about the basic unit it actually works with, the token.
The token, yes. It's the smallest piece of information the AI processes, and tokenization is just that necessary first step, breaking down raw text into these units.
And it's not always a whole word.
Not always. A token can be a full word, sure, but it can also be just a part of a word, like a prefix or suffix or even just punctuation.
But why do that? Why not just use whole words? Seems simpler.
It comes down to efficiency and resource conservation. Think about trying to teach a system every single possible form of every word. Walk, walking, walked.
Right, it would explode.
Exactly. Instead, you tokenize. So if you have walking, talking, and sleeping, you might split them at the common part, ing. This drastically reduces the total vocabulary the model needs to learn and process.
Okay. That must cut down on the computational demands hugely. Our sources had a great rule of thumb for this. Something like you only need about 3/4 the number of tokens compared to words.
That's a good general guide, yeah. And just for scale, an advanced model like ChatGPT 4, it uses roughly 100,000 tokens in its vocabulary. Still huge, but manageable compared to every word form.
Okay. So we have tokens. How are they predicted? You mentioned two main ways.
Two main mechanisms, yes. First, there's the masked language model. This one predicts a word anywhere inside a sentence, using the context both before and after the missing word, like filling in the blank. I blank my homework.
Okay, useful. But the real star for generative AI, the thing that lets it write paragraphs, stories, that's the other one.
That's the autoregressive model. That's the engine of creativity, really.
How does it work differently?
It predicts only the next token in a sequence.
Yeah.
Just the very next one. But the crucial part is the loop. Once it predicts that token, it immediately adds it to the sequence it's working with.
So the context grows.
Exactly. It uses that newly extended sequence as the new context and then predicts the next token after that. This continuous loop, predict, add context, predict again.
You know something? I think I am learning something out of this. I'm sure people who are listening to the summary, they are recalling what we learned in the older episodes. I'm sure the summary is useful, but I am learning how to articulate and express the same concepts differently. It's becoming interesting. Maybe my future episodes will be a little more interesting based on what I learned from this. So
And that's the core capability, allowing tools like ChatGPT to generate coherent text, token by token.
That sounds incredibly powerful, but also complex. So how does it actually learn to make those predictions so well? This is where it gets really interesting for me. how these models seem to absorb like the collective knowledge of humanity without someone manually labeling everything.
Right. And we need to keep stressing that distinction. The AI isn't thinking like we do.
No, it's making a probabilistic guess.
A guess about the next token based on patterns. The completions are predictions, not facts it knows to be true.
Okay, got it. So how did we get past the old way of training? You mentioned supervised learning.
Yeah, for decades, training AI relied heavily on supervised learning. And that meant intensive, expensive human labor. You literally needed armies of people
Doing what?
labeling data, marking thousands of emails as spam or not spam, manually drawing boxes around objects and images and labeling them cat, dog, car, labeling credit card transactions as fraud or not fraud.
Wow, that sounds like a huge bottleneck.
It was a massive limit on the scale AI could reach. The human input itself was the problem. But then, around 2010, maybe a bit later, the industry shifted to something called self-supervised learning, or SSL.
Self-supervised, okay.
This was the absolute game changer because the model could essentially generate its own labels from the data it sees. It removed that human annotation bottleneck almost entirely.
Okay, hold on. How does it generate its own labels? That sounds a bit like magic.
It's conceptually very simple, actually. If you take a sentence that already exists on the internet, say, I love street food,
Okay.
and you
What's interesting is I myself am absorbed in this conversation. I'm listening so carefully, and the the way they articulate the accent and the just the beautiful narration, it actually keeps me very engaged. I'm just listening like you are listening. So very interesting.
just temporarily remove a word. Let's take out food.
Right.
The missing word food effectively becomes its own label. The task for the model is simply figure out what word goes back in that blank to reconstruct the original sentence.
So it knows the answer because the answer was already there.
Exactly. By doing this process, masking a word, predicting it, checking against the original, billions and billions of times across basically the entire internet, the model internalizes grammar, meaning context, all without explicit human instruction. It teaches itself by, well, playing this massive game of fill in the blanks with its own input data.
That's incredible. So that self-supervised part, that builds the raw intelligence. That's the pre-training stage.
That's the pre-training stage, yes, where the model just digests that vast ocean of text, learning the general structure of language, acquiring its raw intelligence. But that's not the whole story.
Okay, what comes next?
Then comes the post-training stage. This is where we refine and align the model. This stage often uses techniques like reinforcement learning, often with human feedback. RLHF, you might have heard of it.
Right, reinforcement learning from human feedback.
And the goal here is to shape the model's behavior.
What's interesting to me is that it's not just basing everything on what we have spoken in earlier episodes. It's actually filling in things. It's bringing in its own interpretation or way of articulating that topic. So I get to hear some different ideas of how do we express a certain topic. I hope you're enjoying as well. I think you should go back and listen to the episodes we have, the previous ones. You will see the big difference between how I talk and how the AI is expressing it. I mean, of course, the accents and the words are different, but then even the way it tries to capture that concept in its own words, it's quite different. Some of the examples are different too.
To teach it what kinds of things it should say, and importantly, what it shouldn't say. To make it helpful, harmless, honest.
So if pre-training teaches it how to speak based on internet patterns, post-training teaches it what's appropriate to talk about.
That's a great way to put it. And then finally, when we actually interact with it, its specific output is often decided by something called sampling.
Sampling?
Yeah, how it chooses the next word. If you use what's called greedy sampling, the model always picks the single most statistically likely word.
Which sounds predictable, maybe a bit boring.
Exactly. It leads to very predictable, sometimes mechanical text. To get that creativity, that spark, that diversity that makes the model sound more, alive, we use other techniques, things like adjusting the temperature or using top K sampling.
And what do those do?
They essentially introduce a bit of randomness. The model might choose the second or third most likely word sometimes instead of always the top one. This leads to more interesting, human-like, and often more creative responses.
Okay, so we've established the foundation, intelligence built on tokens, prediction, and this amazing self-supervised learning. If that's the fuel, The structure that makes it all hang together, the engine itself, is the transformer architecture.
The transformer is the breakthrough. Absolutely central. Before it came along, introduced in that seminal paper in 2017, the sequence-to-sequence models had a really severe bottleneck.
What was the problem?
Well, the encoder part would read the whole input sentence, right? But then it had to compress all that rich information, all that nuance, into a single static context vector. Just one fixed summary.
That sounds limiting, like trying to answer detailed questions about a huge book just by reading the blurb on the back cover. You lose everything.
That's a perfect analogy.
Yeah.
Because the decoder part then had to generate the entire output based only on that one compressed summary. It couldn't easily look back at specific parts of the input.
Okay, so how did the transformer fix that?
It solved it with the revolutionary attention mechanism. This is the core idea. Attention allows the model, as it generates each word of the output, to look back at all the input tokens simultaneously and decide mathematically which ones are most relevant to the current word it's trying to produce.
So it can pay attention to the important parts of the input.
I hope you guys are enjoying this as well, because it's very nicely explained. Even I am kind of enjoying the way they're explaining the topic. It feels like a discussion between a host and a co-host, and you're just part of it. And the richness and the articulation part of the discussion is so nice and so natural that I kind of forget that it's all AI. What a future we are in.
Dynamically.
Exactly. When it's generating, say, the third word of a translated sentence, it can look back at the original sentence and decide, okay, these two words in the beginning are really important for this word I'm generating now.
How does it decide what to focus on? Is it just guessing?
Not guessing, it's calculated. The focusing mechanism is built on three conceptual vectors for each token: a query, Q, a key, K, and a value, V.
QKV. Okay.
The core math involves calculating relevance by essentially comparing the query of the current state, like, what information do I need now, with the keys of all the previous tokens, what information do they represent? This comparison is often done using a mathematical operation called the dot product.
A dot product. Why that?
Think of the dot product here simply as a measure of similarity or relevance. It generates a score. A high score between the current query and a particular key means that the token associated with that key is highly relevant.
So it gets more attention.
Precisely. That token's value vector gets weighted more heavily in the calculation for the next step. It contributes more influence.
That sounds...
I actually want to go back to my episode on transformers and attention and see if I've done a good job, because the AI has done such a good job. I don't know. I don't think I've done such a good job. I should go back and check it out.
Sounds incredibly powerful, just that mathematical assessment of relevance. And I read the architecture takes it even further with multi-headed attention.
That's right. Instead of just calculating attention once, the architecture splits those Q, K, and V vectors into multiple sets, multiple heads. Llama 2.7b, for example, uses 32 heads.
Wow. Why do that?
It allows the model to attend to different aspects or relationships in the input simultaneously. One head might focus on grammatical structure, another might crack subject-verb agreement across a long distance, maybe another focuses on the overall sentiment. It leads to a much richer, more nuanced, kind of multifaceted understanding of the input.
Okay, but before any of that attention magic happens, the raw tokens have to be processed first, right? The embedding block.
Yes, absolutely. The embedding block takes those raw tokens, which are just identifiers, and converts them into dense numerical vectors, high-dimensional lists of numbers that capture some aspect of the token's meaning or usage.
And crucially, it also has to include position, doesn't it? Positional embedding.
Yes, that positional embedding is absolutely key. It encodes the position of each token within the sequence. Without it, the model wouldn't know the difference between dog bites man and man bites dog.
Which is kind of important.
Fundamentally important. The ability to understand that order matters, that the sequence changes the meaning, that comes from positional embeddings being added to the token embeddings right at the start.
So, okay, we've gone deep into the architecture. What does this all mean?
I can't help but notice that it took such a technically dense topic like the transformer architecture, and the host and the co-host were able to kind of build up a beautiful explanation. And it's even hard to imagine that there was no real people. It was all AI. I mean, the words was learned, the language model learned the words, the multimodal model learned the audio bytes, and it understood voice. So it all came together. It's like amazing.
for the tools we actually use every day. How does this foundation token, self-supervision, attention translate into building real-world AI applications?
Well, one big direction the field is moving in now is towards multimodal AI.
Multimodal, meaning multiple types of input.
Exactly. Integrating text, images, audio, maybe even video, all into one connected system. The idea is to build systems that learn more like a child does,
How so?
Well, you teach a child what a cat is by showing them a picture, maybe playing the meow sound and reading the word CAT. The child connects these different sensory inputs. Multimodal AI aims to do something similar, learn relationships across different types of data.
Interesting. And when we interact with these models, the simplest way is just prompting, right? Asking a question, giving it text.
Prompting is the direct human input. Yeah, text, maybe an image now, or audio. But for more advanced uses, especially in business, something called retrieval augmented generation, or RAG, is becoming really important.
Retrieval augmented generation. Okay, what does augmenting generation mean practically? Is it just like sticking a database onto the AI?
It's more sophisticated than that, but that's the gist. And RAA is essential for many enterprise applications. It basically connects the foundation model to an external, often private and up-to-date knowledge base.
Like company documents, product manuals, FAQs.
Exactly. So when you ask a question, the system first retrieves relevant information from that specific database, and then it feeds that retrieved information, along with your original question, to the language model to generate the final answer.
So the model isn't just relying on its, say, 2-year-old pre-training data. It can access and incorporate fresh, specific, external facts.
Precisely. It helps maintain factual accuracy, relevance, and allows it to use proprietary information it wasn't trained on. This brings us to the two kind of distinct sides of AI development we see emerging.
Okay.
On one side, you have model development. This is mostly the realm of researchers, ML engineers. They're focused on the really hard problems. Cleaning petabytes of data, actually training these massive models, optimizing how fast they run the inference, using frameworks like PyTorch or TensorFlow.
Deep in the weeds of the model itself.
Very deep. Then the other side is application development. This looks a bit more like traditional software engineering, but with AI components.
What do they do?
This team selects the right foundation model for the job, designs the user interfaces, it engineers the prompts really carefully, manages how data is stored and retrieved, maybe setting up that RAG system, and then deploys and scales these AI-powered services in production.
So using the models rather than building them from scratch.
Mostly, yes. And the fundamental shift here, the really big change for developers, is moving away from purely deterministic code, where you write exact instructions for every outcome, towards, well, probabilistic reasoning. Meaning you're guiding systems that learn from experience and make predictions, rather than just executing fixed rules. It's becoming more about steering complex systems than just programming step-by-step instructions.
Wow. It's been an incredible journey today. We went right from the LLM core down to the smallest unit, the token, through that amazing self-supervised learning process, and then deep into the attention mechanism, the heart of the transformer architecture.
And as we wrap up, it really does circle back to some almost philosophical questions that this transformer architecture, particularly attention, raises, doesn't it? Well, when these machines perform feats of prediction and attention that seem so similar to what humans do, I mean, this ability to mathematically decide what matters and what to focus on, it does get a little spooky.
You think it mirrors consciousness?
The mechanism certainly mirrors an aspect of our own consciousness, that calculation of relevance, using something like a dot product to weigh importance. We do that too, right? We constantly filter a flood of sensory input, deciding what to pay attention to and what to ignore.
So if intelligence at some fundamental level is about knowing what matters most, and the transformer learns to do that mathematically through attention, it really does make you wonder about the nature of our own awareness.
It absolutely does. And maybe a provocative thought to leave you with is this. Consider what the next iteration of AI architecture, whatever, builds upon or refines this concept of attention might tell us.
What it might reveal about how humans perceive meaning.
Exactly. Or awareness itself. If the goal becomes simply building better and better attention calculators, maybe the gap between machine intelligence and human cognition is more about scale and complexity than some kind of unbridgeable qualitative difference. Definitely something to chew on. Indeed. Until our next deep dive.
That was a fantastic summary of the last 7 episodes. When I started the series, I was a little hesitant to know I mean, to really go deep into these kind of topics. It's not common to talk about it every day, but I'm sure that there is an audience, somebody who wants to go do a deep dive on this. And this particular summary episode, I think, is really the best of the episodes. It's kind of ironical. I don't like my own episodes, but the AI episode, the summary, it's fantastic. So let's see. So next week we'll continue our discussions on other topics, and we will have one more summary at the end of next week. So till then, enjoy learning. Have a great weekend.